Hi, welcome to Unlock Filters Theory and Simulation. So in this video we'll see the second order RC low pass filter. This is a general transfer function of a second order filter. So as you can see here now, this omega naught happens to be the cutoff frequency of this second order filter. Q happens to be the pole quality factor. And this on the numerator you can see there is a a2 s square plus a1 s plus a naught. So this is a very general transfer function. Depending on the coefficients of s, that is a naught, a1 and a2, we're going to have different filters like low pass filter, high pass filter, it can be band pass, band reject, or it can be all pass filter. So that depends on what are the coefficients of this a1, a2 and a naught. So which is 0, which is non-zero, all those things. So we'll move on to the location of poles here. If you can see here, this is the transfer function of a general second order system. If you can see, the denominator of the transfer function always corresponds to the characteristic equation, which certainly shows the position of closed loop poles. If we take the roots of this quadratic equation, the two poles are on the complex, so it's on it will be always complex. If you can see, the real part is away from the imaginary axis by omega naught by 2x, whereas the this is located with a radius of omega naught. So as the value of q changes, the location of poles will change on the s plane. So this is a general movement of pole. The pole can be moved depending on the value of q as well as omega naught. Okay, let us go to very specific second order low pass filter. So this is a general transfer function of a second order system. If you can see here, so this general transfer function reduces to this exact equation for the low pass filter. In this case, you can see there is a a1, a2. So these two coefficients of s will be 0. So it will be left out with only a naught and the denominator. That's what is over here. So you can see a naught by s square plus s into omega naught by q plus omega naught square happens to be the transfer function. The DC gain of this particular filter, okay, how do we find DC gain is substitute s equal to 0. Suppose we substitute s equals 0 here and here, and we left out with a naught by omega naught square as the DC gain. So this is a transfer function of a low pass filter, which is simply making a1 and a2 as 0 in the general transfer function, meaning that there is no finite zero in the transfer function. So we don't have a finite zero. So both the zeros are there located at infinity. You can see this is the pole position. What we're going to have, we're going to have only the poles. You can see both the zeros are at infinity. So it's located at omega naught by q, the real part. The imaginary part is again decided by this and omega naught. This is how the Bode plot of this second order low pass filter will look like. If you can see here, this will have a peak, and this will have a slope of minus 40 dB per decade. So having this overshoot or not having the overshoot depends on the value of q. You can see this magnitude purely depends on the magnitude of q. Suppose if q is equal to, well, we'll want to see in the coming slides, okay, when do we have the flat response, when do we have maximally flat response, when do we have this type of overshoot, that purely depends on the value of q. This is the typical circuit diagram that will be used using op-amp to realize a second order low pass filter. You can see we have two RC component, that is R and C. This is again one more R and C. So this is the one which constitutes the two-stage second order low pass filter. Of course, this op-amp having a certain gain of 1 plus RF by R1 will decide the overshoot, that is the quality of the pole is decided by this R1 RF, of course, along with the value of this R and C's. Okay, let us try to obtain the transfer function for this second order low pass filter using the op-amp circuit. So here we are going to use the signal flow graph technique to find out the transfer function. So this is the circuit diagram. So let us try to identify the variables here. So we have variables like, okay, we have Vin as one of the voltage variable, we have I1 as the second, so V1 is one more variable, I2 is one more variable, and this is V2 here, the nodal voltage, and we have the final variable as V0. So this is the listed variable parameters, which is the current and voltages. Now we're going to write the expression for each one of the dependent parameter. This is actually I1. I1 is nothing but the potential difference between across this resistor, that is V in minus of V1 divided by R. So that's what we have as the expression for I1. Similarly, we write the potential difference across this capacitor is V1 minus V0, because this is V0 here. So this potential difference is proportional to the reactance offered by the capacitor, so that V1 minus V0 can be written as I1 minus I2 into the impedance of the capacitor. Similarly, we can write the expression for I2 as V1 minus V2 by R. Similarly, for V2 you can write the drop across the resistor C. So that's what I have here. And finally, we write the output V0 is equal to the gain times V2. So we have an input voltage V2 here. So that multiplied by gain happens to be the output voltage. So using these expression for the different dependent variables, we can form a signal flow graph which exactly has all variables here. You can see there is a V in I1, V1, we have I2, V2 and V0. So by looking at this, we can construct the signal flow graph, and then we can see now. So we have identified the forward path. There is only one forward path here. The forward path gain is given by 1 over R into 1 over CS into 1 over R into 1 over CS into AF. This is the gain of the amplifier. And we can see there are 1, 2, 3, 4 loops. So this is 1 plus. This is loop 1, loop 2, loop 3. And of course the fourth loop is the bigger one, that is 1 over R into 1 over CS into AF, and there is a positive feedback is there. That's why we have the term which is negative here. The other 3 loops are having negative feedback, that's why they are all plus. You can see now we have 2 non-touching loops, that is 1 over RC into minus 1 over R multiplied. Okay, and these are the 2 loops which are not touching here. So that's why you have the term which is, again, this is the term corresponding to a pair of 2 non-touching loops. And then we can simplify this to get this expression V0 by Vin. This is the final expression for the transfer function of a second order low pass filter with op amp. So it is given by AF divided by RC whole square multiplied by A square into this particular equation. So let us try to compare this equation for the op amp with a generalized expression. So this is what we have. This is a general expression. This is the expression what we got. From this, equating the coefficients of s power 0 and s square, we can come to know that, okay, there is a quality factor Q is given by 1 over 3 minus AB. Of course, the cutoff frequency is given by 1 over RC. Similarly, the cutoff frequency in hertz will be 1 over 2 pi RC. The closed loop gain of the op amp is 1 plus RF by R1. So this is how do we able to obtain the quality factor for this particular circuit, which depends on the value of AV. Suppose if I change the value of AV, the quality factor changes. Once quality factor changes, naturally the overshoot of the frequency response of this filter will change. This is exactly what we're going to do here. So we're going to analyze the Bode plot of low pass filter. So as the value of Q is less than 0.7, which corresponds to a gain of 1.586, we'll have a poor flat response. It means we are supposed to have this to be flat till omega naught, and it should come drastically down. That is the ideal low pass filter. But actually what happens is till omega naught it should be flat, and then it should have a decay of minus 40 d per decade. If the gain is less than 1.56, we'll not have a very good flatness. So to have a maximally flat response, if the gain is 1.56, which corresponds to a Q factor of 0.707, which will give a maximally flat response. If the value of gain of the op amp exceeds 1.56, we're going to have an overshoot. So which corresponds to a Q value which is greater than 1 over root 2. So 1 over root 2 corresponds to 0.707. So if you can see here, this overshoot will be 0. You have the value of Q less than 0.707 or equal to 0.77. There will be no overshoot. We'll be observing the same thing in 20 sim simulator also. You can say this is using 20 sim simulator. So let us assume the value of omega naught to be 1000 radian per second. So this is what is 1 over RC happens to be 1000 radi per second. For maximally flat response, the AV has to be 1.56. So let us substitute the values of RC and AV onto this. So we end up with this as the transfer function for a second order low pass filter. Let us go to 20sim and edit the same transfer function and try to get for the pole zero plot and the Bode plot. So let us see the pole zero plot, and just a minute. So this is what we have now. We are looking for, so if you can see here, we have already edited 15840 is the numerator value, and I can see this is the quotient of s square, this is the quotient of s power 1, this is the quotient of s power 0. So with these things you can see the location of poles and zeros. Because if you can see, since the zeros are there at infinity, we can't see that here. You can see the poles are there located at a particular point which corresponds to omega naught by 2 omega naught by q, which is given over here in the expression. You can see here the location of the poles are, if you can see this location, poles are located at omega naught by 2q. So it is omega naught by 2q is the location of poles. So let us go back to 20sim and try to see the response of it. Now let me see the Bode plot of it. If you see the Bode plot of the same, this is the Bode plot. Okay, let me just this is a Bode plot. You can see this is having a gain of 1.586 multiplied by, okay, 20 log of that will be the gain here. Suppose if you see what is the gain of this, so gain of this happens to be 4 dB. Suppose if you change this, so it will have a frequency, a cutoff frequency of 1000 radian per second. You can see here at 1000 radian per second. So it's actually almost equal to 1 dB. So because 1 dB corresponds to 3 dB down here. So this is 4. This will be close to, you can see when this is 1000, you'll get it as exactly 1 dB. So let me just slightly make it. You can see now it is almost 1000. So you are at 3 dB down. So this corresponds to the frequency, which is the cutoff frequency. And of course, if you can see the phase here, the phase is initially 0 degree, and at cutoff frequency phase happens to be minus 90 degree, and it goes to a phase of minus 180 degree as the value of omega increases to infinity. See now here, so you can see initial phase is almost 0 degree. You can see it's almost 0 degree at 10 radian per second. If you keep on increasing, you can see the phases keep reducing negatively, and when the frequency is equal to 1000 radian per second, you can see the phase is minus 90 degree. You can clearly observe here. So this is almost 1008 radian per second. The phase is minus 90 degree. So this is what is the phase. You might observe that in first order low pass filter, at cutoff frequency phase is minus 45 degree, but in case of second order, the phase will be minus 90 degree at cutoff frequency. So like this, we can able to get the 20-sims simulator output for maximally flat response. We shall change the transfer function to different cases of overshoot and non-flat response, and see how does the plot looks like. So it's going to have an overshoot if the value of q is more than 0.707, and if it is less than 0.707, it will have a poor flat response. We will also see the response of LT spice using the circuit diagram. How do we get similar type of analysis for a circuit? So we'll see that in the next video for the same low pass filter.